afternoon, ladies and gentlemen. Okay, so the topic of my presentation is STRATOFLY, the project that has just been introduced this morning by Marco Marini from CIRA. STRATOFLY project, and particularly this afternoon, we would like to concentrate on the main goals, main challenges and goals. Let me just see if, okay. So here is the table of content. I will briefly introduce the STRATOFLY project, then what is the reference vehicle, reference trajectory, and what is our vehicle that we have called STRATOFLY MR3, and what are the main technical challenges, and then I will have some conclusions and future steps. Okay, here is the acronym STRATOFLY, which stands for Stratospheric Flying Opportunities for High-Speed Propulsive Concepts. It has been funded by European Commission. The kickoff has been last year in June, and the project will last for 30 months. What is the aim of the project? The goal is to assess the potential of a hypersonic flight for civil transportation. Civil transportations are meant to be for underwater route, and we are asked also to demonstrate the capability of reaching TRL 6 by 2035. Very important, the project focuses not only on technical issues, but it focuses and cares a lot also on other, let's say, operational issues covering society. So talking about society, let's say also public consensus, economical aspects, and also environmental impact. Here there is a brief video, very short video, that I would like to show you. We have prepared this short video. Yes, it's going to, yes, with some music, sorry. The video that we have prepared for the Aero Days 2019, we were there presenting the project and the model that we have built. Here you have some main objectives, and here are the partners. We are 10 partners all over Europe. Italy, Politecnico Turin, and CIRA. Then we have Germany, Belgium, France, the Netherlands, Spain, and Sweden. The objectives of STRATOFLY are summarized here in this chart. 300 passengers, antipodal routes, shorten. We have the goal, the ambitious goal of shorten the flight time, the magnitude of the flight time of 1 order of magnitude, so 3 hours. And here is the reference vehicle that has been introduced before by Marco Marini. So LAPCAP MR2.4. Performance, 400 tons, a takeoff, Mach 8, and 10,000 cubic meters as the overall volume of the vehicle. Here's the comparison with the other big aircraft. We are a bit bigger than the A380. And here's the internal layout with the duct. Basically, it is a flying engine, we can say, but the engine runs all over the vehicle, from the front to the rear. We know already from the presentation of this morning that we have 6 air turbo rockets and 1 DMR. We use liquid hydrogen, and this is the cabin, where we have the cabin. This is the bubble structure of the cabin with the exit for the passengers. It will be a glass cabin concept, so all future technologies will be employed, so windowless cabin, of course. We are using LA2, so liquid hydrogen. And this is a crucial system that I will talk about later on. This is a mission, two city pairs that might be connected, and this is the nominal mission, the reference mission trajectory connecting Brussels, Europe to Australia in a bit less than 3 hours. Thermal issues are crucial. They've been presented this morning, and this is something about the climate. Of course, this is a very important issue for us, not just technical, but also operational and environmental. So this was a short video. Now I will continue, and I would like just to focus on some key aspects of the project. Okay, here we have the partners, all the partners that are involved in the project. Many partners were already part of the previous consortium of LabCat 2 and LabCat 1 and other. We have some new partners, and here you can see all the different, let's say, competencies of the partners that are spread around Europe. And yes. This is a chart that we have already seen this morning. On the left, on the right, you can see the work package structure. On the left, an interesting picture which summarizes the technical objectives and the operational objectives. So, on the right, in the bubble where we talk about technical objectives, you can see all the main, let's say, challenges. You can see already the main technical challenges. We have integration and performance, we have lightweight structure, we have supersonic combustion and plasma-assisted combustion, and we do also care of emissions. Emissions, we want to reduce emission, and we want to reduce noise. So noise, of course, is a crucial aspect. Here is the reference vehicle compared with our vehicle. So there has been some changes that were highlighted before in talking about the external configuration. We have redesigned the flight control surfaces and the vertical tails. We are working at the moment on the aerodynamic database because this was one of the issues for our project, but we are currently working on it. Anyway, so this is our heritage. LabCat 2 project is our heritage. And I would just say not just LabCat 2, but also the project, European funded project that came before LabCat. So there is a number of them: LabCat, LabCat 1, LabCat 2, Atlas, Icari, many projects, so many millions of euros that were given to this hypersonic field. And we would like really to build on this heritage, to exploit. That's why for us it's very important to start from a reference vehicle. So we are starting from this vehicle and we are going to refine the design. The design taking care also of operational aspects, environment, public consensus, economic feasibility of the vehicle, which is of course very important. The reference trajectory, this is the reference trajectory. So Europe, Australia. It is an antipodal route, but there might be other trajectories, of course, of interest. In the table at the top on the right, you can see other examples of city pairs all around the world. We want to exploit some technical, let's say, some technical capabilities related to the hydrogen, liquid hydrogen that is our propellant. So we are, for our technical outcomes, we are considering antipodal route, not short route. However, this trajectory is absolutely, let's say, fine because it is not flying over any land. We know that we can have serious problems, especially when we are, let's say, taking off and then landing up to reaching Mach 1 and up to reaching supersonic flight. There are a number of studies from NASA, but also other European-funded projects that are trying to solve the issues of flying supersonic over the land. So this trajectory is fine from this point of view, but there are other possible trajectories that we would like to consider. Our configuration, the external configuration. So I already said what are the, let's say, the differences with respect to the LACA, to the reference vehicle, from the point of view of the external configuration. Anyway, we are currently investigating the possibility of varying the overall volume and the overall mass of the vehicle. So we would like, our starting point is 400 tons and 10,000 cubic meters, but we are investigating different possibilities, evaluating, as Marco said this morning, the possibility of switching again on the engine when we are landing. So a power landing. In the previous LACA 2, the landing was unpowered. We would like to give the possibility also for safety reasons to power again the engine when we are landing, and this means additional propellant, of course. This is one thing that we are taking into account, but we are taking into account also, let's say, technological improvements from the point of view of tanks efficiency, and also propellant, the density of the liquid hydrogen. So these are technological enhancements that we are considering in this analysis of the overall volume and mass. So mass budget and volume budget. The inside, the internal configuration. If you look at this picture, it is quite clear that most of the volume, I would say a great part of the volume, is occupied by tanks. Bubble structure tanks all around the vehicle to host the propellant. You can also see underneath, at the bottom, let's say, you can see the red cabin that you saw in the video. All along the vehicle you have the duct, so the air duct for the inlet, combustor and nozzle. But then there are other subsystems, so it might be evident from this picture the propellant system, the tanks, the cabin and the duct, so the propulsion subsystem. But we do have a number of other systems that were not considered in the previous project, and we need to consider all these subsystems to have an integration, a complete integration to assess the feasibility of this vehicle. So what are the other subsystems? Of course, the landing gear. We need to find some room to host the landing gear when it's retracted. We have this thermal and energy management system. I will talk about it in a minute. The environmental control system for the passenger. Thermal protection system. We need some form of thermal protection system, and also the avionics system. What are the challenges? We know now what are the systems that make up this vehicle. What are the technical challenges related to the systems? First of all, propellant system. A huge amount of propellant has to be stored in these tanks with bubble structure. One of the goals is to assess really the feasibility of of tank efficiency and liquid hydrogen density. moving to better value, better performance for the tank efficiency and liquid hydrogen density with respect to the state of the art would really help us to keep the same budget for the mass and volume and performing antipodal routes with power landing. The cabin will be a windowless cabin, so we need to consider the all glass cabin technologies. Public consensus shall be assessed, and also the cockpit. Cockpit, the same. We will talk of virtual cockpit, or what if we don't have a cockpit at all? That could also be an option. In the CESAR program, looking at the far future, the CESAR program, European, again, one European big initiative, in the far future, large passenger aircraft could be autonomous aircraft. So who knows? Who knows? So this is something that we have to keep in mind. I mean, we have to be aware that there are plans that are looking at the future without a cockpit, without pilots on board. So we need to think of that, at least to keep it in mind, and then decide that no, it is better to have the pilot, but at least we know. Okay, this is one of our biggest challenge, the thermal and energy management subsystem. This system is I would say that is one of the most significant examples of integration of different, totally different subsystems on board a vehicle. Which are the systems that are integrated within this one that is represented in the picture? We have the propellant system, because the core is liquid hydrogen. Liquid hydrogen as boil-off. We talk of the boil-off. We want to exploit the boil-off of the liquid hydrogen, and we want to exploit also the liquid hydrogen as a liquid. So the propellant system integrated with the propulsion. Is this okay? The propulsion system. Here there is a combustor. We have the thermal control system integrated in the picture. You can understand it from some heat exchangers that you find all over the vehicle. The coolant fluid in the heat exchanger is the liquid hydrogen, our propellant. This is nothing new for aeronautics, but the novelty here is the propellant. The environmental control system, which is where the heat exchanger of the environmental control system are cooled by the liquid hydrogen, and the electrical power system. In fact, the name of the overall system is thermal and energy management. So the electrical power system, why? Because we have a turbine here that will drive generators, electrical power generators. What is the let's say, power budget of this vehicle? We are talking of megawatts of power. We haven't really investigated. The project is still in the middle, not yet in the middle. So we need to investigate the electrical power system, but this is the idea. So, big challenges come from this very highly integrated subsystem. Other challenges are coming from the environmental control system. The air pack, or cold air unit, where is coming from the air? The air is coming from the intake, the air intake for the engine. And we need to assess if we need a compressor driven by electric motor to compress the air if we need, but we need to assess this. And what about the impact of the air breathed by air duct onto the engine performance. So we need to assess this. Of course, bubble structures are another big challenge all over the vehicle. We have the cabin in bubble structure, we have the tanks, and so on. Other challenges, thermal protection system. Thermal protection systems. Marco Marini from CIRA this morning said something about that. We cannot just use CMC as a, let's say, protective material for the leading edges. Maybe it will be not enough, and we might need heat pipes cooled leading edge. So heat pipes integrated in the leading edge, which can use as cold source propellant and as a working fluid, let's say a material which is actually solid at sea level. So we need to investigate also this. The propulsion system, of course, is a big challenge for us, but we cannot forget about the avionic. We cannot forget about the avionic. We have already mentioned all the glass cockpit or glass cabin technologies that will be included in the cabin or cockpit, but we have to keep in mind also the future air traffic management, so the 4D capability to fly in the future air traffic management, and so our aircraft shall be equipped with the necessary, let's say, equipment for communication, navigation, and surveillance. This is our, let's say, roadmap. We still have to complete the roadmap, but we need to get to 2035. We would like to demonstrate that we are able to get to 2035 with TRL6 for the overall vehicle, and what's next, we will see. This is the academy. Marco Marini will talk tomorrow about the academy. Just to say that students are involved, are very welcome in the project, and we have some students coming from the University of Naples that are part of our initiative to disseminate the hypersonic, let's say, passion. So this is good. And we have students coming from all over the world, actually. And these are some pictures from the Aero Days, the model that now is shipped. And this is, yes, thank you.
Thanks. So Viola, do you have questions?
This question is a passenger-centric question. Did you study the level of physical stress so that can be tolerated by a normal passenger, or do you need special medical exams before accepting the passengers on board?
Thank you for your question. This is a crucial aspect, because of course we don't want any, every people has to be able to be on board this aircraft. We don't need let's say, trained people, or so there must be no limitations at all. We will be studying this in the next few months. Germany will be DLR, will be studying this, the effect on the human body, because it might be very stressful to travel from Europe to Australia in 3 hours time. So. And also, I would say the cabin is still something that needs to be assessed. Yes.
Yes, because there is also a psychological problem,
of course,
and the physical problem, both of them.
Yes. Yes.
Do you have a package related to regulations? Do you intend to use active regulation? You're looking for new regulations?
We are looking for new regulations. That would be nice to give at least we would like to give some suggestions maybe, but so far we have considered some regulations, for example, for the exits, the doors of the cabin, to let the passengers enter the cabin and exit the cabin. So the number of doors of the cabin that you have seen in the picture are not just there. Also the size depends, it's according to regulation, the size, the numbers, and let's say the location of the doors that you have seen. Actually, it depends on the shape of the cabin, because the cabin is, let's say, it has 3 different levels, so for safety. So far we have considered some regulations just related for the cabin, but we know that is an open is an open question.
If I may, just another small question. Number of passengers. 300. Yeah, but why? I mean, do you have, a reason for that? Why not 200 or 400?
Well, we have, this is something that, first of all, comes from the, for us, it was an input for our project, because it comes with the reference vehicle of the previous LACA 2. There were, anyway, a number of trade-offs were made in terms of passengers, number of passengers, and also in terms of Mach 8. Why Mach 8? Why not Mach 5? So these were typical trade-offs that were made. And one thing that I can say about the passengers is that if you decide to have, from a technical point of view, if you decide to consider, if you want to consider 200 passengers instead of 300 passengers, and you say, okay, maybe I will gain a little bit more of fuel, but this is not so much. I mean, the percentage, the additional fuel that you can have on board, if you decrease the number of passengers of 100, is not so much. So it's not really worthwhile. And so the consideration about the passengers can be technical, it can be also economical. In fact, we are trying to assess the business case, because this is also important. There might be...
My question was just was quite the same. Why 300 passengers? But I have another direct question. Is that kind of embedded engine or flight engine scalable? Is it possible to think about a 30 passengers vehicle, or 3 passengers vehicle, or no passengers? Can I have one of these very small?
No passenger is Exafly, but no passenger.
But it's just for to stimulate. Why is this kind of engine scalable, or there is some physical characteristics that makes it?
Well, this is a good question. The duct that is all over the vehicle, from the front to the rear, it comes. We have really taken we have taken it from the previous project, and we haven't modified, because it was a result of optimization made by von Karman Institute, CIRA, and DLR. So we are changing all the CAD model. We are making it really modifiable, but this is something that we are not going to modify. So it really is the performance of the propulsion system are heavily affected by the duct.
Only because the duct is an input of the project, but anyone has studied this duct and
of course you can yes, but you will need to let's say recalculate and re-optimize it.
Of course. It was just curiosity.
Yeah.
Okay. Thank you very much.
Question?
Thank you. It was a very interesting presentation.
Thank you.
Before you just mentioned what do you call it, LACA experience.
Yes.
I really wonder, because it sounded like a dream. I see Rino now. What remains, not actually of the lab cat and festive experiences, but actually of the MS program, which was one of the dreams of the great scientist Luigi Gerardo Napolitano and many others actually. What remains of their experience? And in particular, what remains not only on the scientific and industrial, but all on the, according to your perspective and your point of view, what remains of their experience and the past experiences on the human side, on the human point of view. This morning Gianni Candotti mentioned the fact that already more than 50 years ago we had the X-15 experience with more than 200 flights. So basically he spoke about Shepard, Walker, and now what remains of that experience, on those experiences, of that dream actually, from the human perspective rather than on the industrial / scientific experience. Maybe you're pretty young as we are, and so, but...
Sorry to interrupt. We are playing on our 15 minutes break. If you can make your question short, and then we'll resume discussion afterward. Thank you.
No further.
Okay, no, just a very short answer. I think that this type of project allow us to continue the dream of hypersonic, from the F-15 to the Apollo shuttle and so on. We would like to continue to dream and eventually to get to something really operative, because it's time to move to something really real, you know? And so let's see. Okay. But
Sorry, I don't have time for more questions. So, 15 minutes, please.
we can